Okay. Well, thank you. So I'm very grateful to the organizers for inviting me to this beautiful place. Thank you. I think so. It's a shared course with Ali Altug. The emphasis on the emphasis all will be on Ali's talks. So I think my subtitle should be kind of preparation for beyond endoscopy. So I will try to just do that. So it's kind of, I would say before endoscopy, but that will be incorrect. How am I doing? And well, since I want to say kind of roughly what we're preparing for, so even though that's not at all what I want to talk about, that's what Ali will talk about, so he'll probably repeat it, and he will also give some interesting history of that. Okay, I'm getting some lip syncing about speaking louder. Is that? Slowly. Everybody heard except for me. That's no, I will slow down when I write things down. So anyway, so basically, okay, let's summarize what I just said. So Ali Altug will do all the real work. Okay, since I want to say what I'm trying to do preparation for, I will say something. So I'm doing it by plagiarizing Ali's lecture that I heard earlier. So, okay, so what's the point? So, but basically, so all my lectures will be really about orbital integrals. And there are some subtleties about what kind of measure you want to think of when you're computing an orbital integral, and so that's what I will mostly focus on. But before I get there, I want to say a few words about beyond endoscopy, just to give an indication, you know, where this is heading, rather than do a lot of technicalities with no motivation. But this motivation will, I think, get repeated. So, and also this hopefully will provide a bunch of examples for the trace formula lectures of what happens on the geometric side. So I'll try to be very concrete and quite elementary, and we'll do examples. That's kind of the idea. Okay, so so what is beyond endoscopy? Where is it going? So, well, I don't really know, but here's what I can try to say. So, so this beyond endoscopy, which I will abbreviate to BE for today, is an idea of Langland's on how to attack the principle of functoriality in general. And he called it a pipe dream in a paper from 2000. There is also a very interesting subtitle to that, which Ali will explain. You will see why Ali should be explaining that. So, okay. And so, very roughly, and so I'm going to ignore all details, partly because some of it are not known, and partly because it's not really what I want to focus on. But so everything should be taken in very big quotes. I would use quotes when I'm trying to say something approximate, so big quote opening for now. So suppose, no, I will write everything down. Everything we're saying, I will write down. Okay. All right. So Langland's functoriality conjecture. This is a real challenge. The speed thing. Okay, so very roughly says the following, that if, so suppose you have G and H reductive groups, and well, Langland's dual group already appeared. For my talks, it's going to be completely unimportant what it is, so I'm not going to explain anything about it, but suppose you have an embedding from the Langland's dual of H to the Langland's dual of G. So suppose you have some nice homomorphism. Well, actually, maybe it doesn't even have to be an embedding. So then there should be a transfer of packets of representations of automorphic representations from H to G. So by H, some automorphic packet, you can think of a packet of automorphic representations of H should correspond to a packet of automorphic representations of G, such that, of course, many compatibility conditions hold, but in particular for L functions. So, okay, for every finite dimensional representation rho from the Langland's dual of G to some finite dimensional vector space, we have the equality of L functions. Sorry. So if you have a rho from, so the dual of H maps to the dual of G maps to GLV, so you can compose the parameters. And this should be the L function of S by G rho. So some other conditions need to hold. By the way, we just heard the lectures this morning about whether, what is even the definition of these L functions, right? At almost all places, you have a good definition using Arthur and L functions, but, what happens at those finitely many primes? So all of this should be taken as very conjectural. So, but okay, ignoring this. So suppose you have functoriality and suppose it holds somehow. Then the question that, so Langland's idea of how to approach this is to say, well, so at the moment everything is conjectural, right? The classification of the packets through Langland's parameters, which should yield this functoriality, is all conjectural, right? Oh yeah, maybe I should say this about parameters. So why should we have such a transfer? Well, it's because, again, conjecturally, as part of this whole philosophy, the automorphic representations correspond the automorphic representations come in packets. That are parameterized by this conjectural automorphic Galois group. So this is again locally, of course. Many instances of this conjecture are known, but this is. So this, I would kind of, just for the next 2 minutes, and then I stop talking about these things, I would call these, so this automorphic Galois group is an unknown, non-existent object at the moment, but suppose it should be there, and there should be Langland's parameters, right? And these parameters should parameterize the packets of automorphic representations. And then, of course, if that was the case, then if you have this situation, so there is this automorphic Galois group, then the representations of H are parameterized by maps from it to the dual of H. Now, using psi, it maps to the dual of G. And then, of course, by composing, you will get the parameters for G. And so, in this world, it seems that this group is even more conjectural than many other things. So an idea is to say, well, suppose we don't know what these parameters are like at all. We don't even know what the source of these parameters is. But maybe we can describe the image of these parameters. So the idea is to describe the image of the functorial transfer from H in terms that are intrinsic to G, without actually knowing the parameters. Okay. So, so more precisely, one could sort of look at the parameters, so we can sort of classify these Langlands parameters according to their image. So kind of on the top, you will have the parameters such that its image is actually dense in LG. So this is the closure, the topology of G. Remember, this is basically a complex group. And so, and then you will also have the ones, so for each H, as above, for each H such that the dual of H embeds into the dual of G. You will have the parameters whose closure just fills up the image of the embedding of this dual of H into the dual of G, right? So this would be some smaller dimensional subspaces. And so you could try to detect kind of the smallest H for which our represent. So if you look at the automorphic representations for G, you could try to detect which subgroup H with this property did it come from by transfer. So, okay, let's leave the hike announcement up. And so the good news is that Ali will probably say it all over again with some detail. But, okay. So the next idea is to detect the representations, the automorphic representations of G that came from H by transfer for each H that satisfies this property, that its dual embeds into the dual of G. Okay, and so more precisely, so the aim is to have a stratification. So kind of, I'll put it in quotes because it's really a very rough statement, but roughly speaking, we want to stratify the usual L2 space according to these images. So we'll take it as a direct sum over all pairs of an embedding from the dual of H into the dual of G up to conjugation. So this is conjugation inside the dual of G. And here is the image of a pi such that the closure of the image of phi pi is sigma of LH, multiplicity of pi times pi. So these are representations of G, right? So this is well, one has to worry about discrete. So maybe I should say discrete just for safety for now, because otherwise you wouldn't have a direct sum. But well, at least let's say maybe we just want to say that just get the discrete spectrum to be this decomposition. One has to start dealing with non-discrete things as well. Ali will have to deal with this somehow. So so that's roughly the idea. And now, so this is kind of idea number one, is that's what we want, is we want to have this stratification, but the point is that we don't have these parameters at all. We're not going to try to have them. So how can we try to have this stratification? So the key idea here is to use the trace formula. So I think what's now called beyond endoscopy is a program to establish this kind of stratification. So maybe you want a candidate stratification of this kind. Without any reference to these parameters, but instead using the trace formula. Okay, so now what does the trace formula have to do with this? Okay, so so before we get to the trace formula, just kind of one little interlude about these L functions. I haven't yet erased it. So, so one wants to detect transfers from H. So the representations that came from H. And if we had the L functions, and if everything worked, and if all the Langland's conjectures held, then the candidate for describing these transfers from H would be a reasonable candidate would be just to look at a pole of the resulting L functions. Why is that? So the point is that the pole, existence of a pole at S equals 1 of L of S by G rho for some rho should detect whether pi G came by such a transfer. Why is that? It's because on the Artinel function side, so okay, I'm just gonna, I'll leave the equality of the L functions that characterizes, that should hold if pi came by transfer from H, so I'll just leave this up. And so now, okay, so now suppose you had this conjectural automorphic Galois group, so you had a parameter that goes to LG. I had a parameter phi pi H that goes to LH. So you have a homomorphism psi here. So suppose the closure of the image of phi pi is LH. So then, what do you want to say? Oh yeah, okay. So right. So then, if we have these L functions, then in particular they should relate on the other side to the Artinel functions of the parameters. And for Artinel function, yeah, maybe let's put this down. So for Artinel functions, the order of the pole at S equals 1 is the multiplicity of the trivial representation. Oh, I've got this diagram again. Anyway, it's the multiplicity of the trivial representation in the restriction of rho to the image right. So we know that for Artinel functions, that's pretty easy thing to check, and I'm not going to do that. I think maybe it'll show up in Ali's talk, but anyway, it's just motivation. The multiplicity of the pole there really just measures the multiplicity of the trivial representation. So now that means that, and so we expect with this picture that if you take the closure of the image of the parameter that gave us our representation, and it turns out to be exactly the Langlands dual of some h that's sitting in G via some embedding, then we expect that, so if the pi of LH bar, sorry, that's not what I meant to say, sorry. Sorry, I wrote down something really dumb. I'm sorry, I'm actually a bit jet lagged. So what I meant to say is that you take the closure of the image of the parameter, and it might be, sorry. Okay, so what we expect is this, that if the image of this parameter fills up exactly the Langlands dual of some h, then the multiplicity, so then you make the, take a representation rho of G restricted to H, and so then we expect that the multiplicity of this pole of the resulting L function is what am I trying to say? Yeah, so so basically we expect that the what am I trying? Sorry, I'll write this down and then right. Okay, right. Sorry, I misspoke. All right, so this is by G. All right, so yeah, so I think that's what's, so what we're doing again, so sorry, I got a bit confused here. So we have this representation into GL of V rho. All right, so on the one hand, we can take our representation pi, which is a representation of G, and form, well, conjecturally, form its L function for any such representation rho. And so, on the other hand, if we know that our representation pi came via this picture by Functorial transfer from H, then the pole of our L function would equal, sorry, the order of the pole of our L function in particular will equal the order of the pole of the L function that was attached to the representation of H. And that, on the other hand, because of the Artin L function situation, should equal the multiplicity of the trivial representation. So this one is the trivial representation. In this restriction, in the restriction of our representation rho to the image of H. All right. Oof. And so the upshot of all of this is that by varying this representation rho and looking at the multiplicity of the pole at 1, you can try to detect whether your representation G came from some H or not. And so and so this pipe dream that Langlands describes back in 2002 is, well, one could try to, so now kind of a bit more specifically, so we want to use the trace formula to isolate the representations pi such that this yet not completely defined L function has a pole at S equals 1 of particular multiplicity. And kind of taking multiplicity into account. Okay, and so this finally, and so kind of quantitatively, what one sort of wants, and again, this is all still just an approximation. So all I've said so far is basically an attempt at motivating what we're going to try to do. And hopefully better motivation comes soon. So, but all right, so what we want is, again, very approximately, is a formula for the sum over automorphic representations of G of well, kind of it's the kind of thing that you would see on the spectral side of the trace formula, right? So let's write this down for a moment. So you would want, so the spectral side of the trace formula is normally a distribution, where you take a test function, right? And then, well, this is kind of the discrete part of the spectral side of the trace formula would be something like this. However, what we want this m pi to be not the multiplicity of pi in the in this L2 space on G, but what we want is this to be the multiplicity of the pole of L of S pi rho at S equals 1. So I'll put it like m pi of rho. So what we want is to somehow do a bit of a different thing. So want to put in multiplicities of the poles here and still compute something like this using something like the trace formula. So this is still just very much an approximation. So and so a little bit more precisely, so well, you kind of need to, so to make it a little bit more precise is, you see, the real issue is the L functions, right? Because as I said, you know, at the moment, only at finitely many places do you have a good local L factor. So that's something that we just heard about this morning. And so in particular, you need to be able to somehow ignore finitely many places. So, so what we want is to fix S as some finite set of places. You could say that it includes infinity so that you can throw it away and not think about what's going on at infinity for a little while. And then you have partial L functions, which are in better shape than the overall L functions. And so then at least you can start writing a formula. So at least, you know, we want to have the left-hand side that's somewhat well-defined. So, so then, more precisely, we really want a formula for a formula which, you know, Ali says is the trace-like formula. So I'm really, a lot of this is kind of quoting Ali's talks anyway. So for the sum over pi of trace of pi s of fs, so this is kind of the usual thing, except done with having thrown away the places from s times m pi of rho. So now this is the multiplicity of the pole of the partial L function, and that's much better. So this one can be well defined. Okay, so at least now we have an expression. So, so the goal of the next, I guess, 10 lectures is to develop some sort of an expression via orbital integrals or whatever we can compute in some sense for something like this. Unfortunately, it's still, so at least now it's a well-defined expression that we want to somehow compute. The idea is that why do we care for something like this is because then you can try to play with the test function fs to isolate a given representation, right? And then you would be in good shape because then you would have something like a formula for the order of its pole. This is unfortunately still not what will happen. So it turns out that in fact, this is not something that you can actually do. You do a little bit of analytic number theory trick, to express this as some logarithmic derivative. Then there is some formula that you want, but you can't have, so you try to have a different formula. Lee will explain all of this, or some of this. But the point is that, okay, we want to have a formula of sorts which is like the trace formula. And the strategy for that, so as I said, I have not finished massaging the expression that you want to get, but I will stop here for now. And the strategy for getting such a formula is to use the trace formula of Arthur, the stable trace formula. In any case, I think so far it's kind of been done for GL2 by Ali, and so for GL2 stable doesn't really matter. For GLN, generally stable orbital integrals are the same. And so to use the stable trace formula and then do Poisson summation, on the geometric side. So notice this is not quite, this is sort of related to this morning's lectures, but it's not quite the Poisson summation that gives you the functional equation for L function. It's going to be a Poisson summation, but over a different space. So, exactly. So, I mean, all of these things are sort of closely related because the matter of basic functions is exactly what ultimately goes into these test functions here. But I think those two applications of Poisson summation are a bit different. So, and so what I'm going to talk about is basically I'm going to, so my lectures are going to be about kind of massaging the, working on the geometric side to kind of prepare it to make it look like we could use Poisson summation. So what do I mean by this? Is, Poisson summation formula is usually something that you do on a lattice living in an affine space or something like that, right? So for starters, we want to interpret the geometric side of the stable trace formula as some sum of things that live on the affine space rather than conjugacy classes of the group. And so that's what I'm going to do. And yeah, what I should have mentioned earlier is that somehow, so what I agreed with Lee that I would do is do the exposition of the paper, of some part of the paper by Frankel, Langlitz, and Go. So there was a paper, so the main reference here. So it's a paper which says basically beyond endoscopy start of a program. So Langlands formulated his beyond endoscopy pipe dream, and then 7 years passed. I think this paper is from 2009. And well, they were able to formulate kind of the beginning of what they would do with the geometric side. And then I think Ali carries it out for GL2, and I think it's now been done for GL3. Okay, anyway, I'll leave it to him. So, so my main goal is basically to explain one particular formula that shows up in this paper, which re-expresses the first intermediate goal is to re-express. Yeah, my first goal is to kind of explain. I would say, it's funny, if you're reading this paper, so I want to explain the formula 331 in that paper, which they actually spend many, many pages explaining, and I will just give an approximate explanation for why I think it makes sense. I will not actually give detailed proof, but I will do examples. So that's sort of the idea. And so which achieves, so this is kind of a conversion of the geometric side of the trace formula to something that looks like a sum of values of some function over a lattice in an affine space. Okay, so this is kind of, so my hope is to do this. This will probably take the rest of today and today's lecture and tomorrow and maybe a bit more. And then I will do an example, kind of I was looking for a baby case, basically, of what can one do. So Ali will do some technical work. And the best baby case I found was the Eichler-Selberg trace formula. So then I'll kind of try to write it down and see what we can glean from that as an example. And then hopefully that'll prepare us to listen to Ali's lectures. So it's going to be basically everything is going to be quite general now. So on the other hand, so at some point I will switch to GL2, but for now this can be done in much, much greater generality, and I don't see why not. So for now I'll just keep working with reductive groups generally until we have to restrict to semi-simple, simply connected or something like that. Okay. And so, all right, so now what does this geometric side of the trace formula look like? So the geometric side approximately, again, ignoring all issues of whether you have elliptic terms, hyperbolic terms, or whatnot. So geometric side, roughly speaking, looks like this. So if it's a stable trace formula, so this is the stable conjugacy. So you're summing over stable conjugacy classes. Things like, I'll call this volume of gamma times the stable orbital integral of f. So what's going on here? So f is a test function, as usual. So this whole thing is a distribution. The volume of gamma is the volume of the centralizer. Like this, right? So here, I guess, I started using the notation where f is a base field. Eventually, it will be the rational numbers, but for now, there is no reason to restrict to that. So the adels are over the field f. I will just omit that from the notation. Okay, and now what's a stable orbital integral? Well, this will get defined, and I'll give examples soon, but I'm sure you've already seen a lot of it. Unfortunately, I missed the first week. Okay, so now all right, and so the first part is a matter of right. So actually, there are basically two things. So first, I promised that I would make something like this look like a sum over a lattice that lives in an affine space, right? And so we have to define this affine space, and this affine space is going to be, well, at least in good cases, is this Steinberg-Hitchin base. So this gives us the affine space that we'll be summing over. And then second, well, I would like to, so this is something that probably wasn't quite emphasized in the lectures on the trace formula because there are so many details already to take care of. But, you know, so we'll have to, let's say, think of measures on the orbits. Right, so when you say an orbital integral, it's of course it's with respect to some g-invariant measure on the orbit. But, so of course such a measure is unique up to a constant. So on each orbit, so of course g-invariant measure and there are somehow, in a way, there are two natural ways to approach defining measures on groups or measures on orbits generally, and I will talk about this at length tomorrow, I think. So the point is that in the trace formula that was stated last week, I guess, there is a particular choice of measures, which is quite natural. But it turns out that if you choose measures that are more related to the Steinberg-Hitchin base, so we will change the normalization of measures, and that will remove all kinds of difficulties. So the orbital integrals that arise in the trace formula have singularities, and so that makes the function very much not amenable to Poisson summation. And also, these volumes, it's not quite clear what to do with that. So it turns out that if you change the measures to measures that arise naturally from the Steinberg-Hitchin base, then kind of a big chunk of the factors that go into this volume and a big chunk of stuff that makes sort of orbital integrals singular kind of disappears. And that's what that formula in Frankel-Langlands and Go does. And so I'm hoping to basically explain what happens there. So change the normalization of measures to a more natural one from the point of view of part one. Okay. All right, so maybe I haven't really stopped and asked for questions, basically because I'm not prepared to answer questions on beyond endoscopy strategy, but now is maybe a good time to ask for questions in terms of a general outline of what we're going to do. So we're going to do this and that for now, and then do a bit more preparation for Elise talks. All right? Any questions about this? So I just didn't want to lose everybody. So in the beginning overview, and I couldn't avoid saying it, but it will be sort of said again with the GL2 in mind, and so hopefully this will all make sense. Okay? Right. So, questions? Okay, so for now, now we're completely down to earth, so I want to define the Steinberg-Hitchin base. And so first, let's just talk about Chevalley map. And now everything is going to be quite elementary, so yeah, I'm told that one shouldn't apologize to the experts, so I apologize to everybody who feels that this is too slow. Okay, so what we want is we want a space that parameterizes the stable conjugacy classes in G. And for now, let's actually, so yeah, it's a very simple observation is that for GLN, stable conjugacy classes, okay, here to start. So of regular semi-simple elements, okay, and these form a dense set in the group, so mostly we can just focus on them. So on the trace form, we'll have to worry about other ones, but for now we won't. So, and regular semi-simple means diagonalizable over the algebraic closure, and the eigenvalues are distinct in this case. It's all very clear. And so they are parameterized in one-to-one correspondence with characteristic polynomials. Sorry? Yeah. Right, sorry. So, yeah, so since I said regular, I have to demand non-vanishing discriminant. Right, and so if you map an element to an n-tuple of the coefficients of its characteristic polynomial, it gives you a map from semi-simple elements. Well, actually, in general, it gives you a map from GLN to the n-dimensional affine space. Well, except, so since we're in GLN, then the determinant, the last coefficient, is not going to be 0, so it's a complement of a hyperplane. And well, there are better ways to describe this, but at least roughly the idea, the prototype, so we'll do this sort of in general, not very much in general, but the prototype is this characteristic polynomial map. So it's a way, and the fibers of this map over almost all points any coordinate. I'm just thinking of a hyperplane. I should really. This is not a good way to write it. Maybe. So okay, and for almost all points, meaning for an open dense subset of points, the fibers are exactly stable orbits. Right? In GLN, stable doesn't do anything. It's the same. And so it kind of, so that basically says that, roughly speaking, the sum is actually already over, is going to be over lattice in an affine space, right? So the affine space is going to be the space of characteristic polynomials. However, I would like to do it a bit more precisely in the generality that's not just GLN. And so let's first, and also, so when I do the measure conversions, I would like to actually do things on the Lie algebra first, because it gives a better idea of what's going on, and then for the group you can sort of soup it up so that it works. So, so kind of the general, so let's just recall how the Chevalley map for the Lie algebra works. In general, right, so so suppose you have well, a reductive group with the Lie algebra G, and suppose for a moment that you're working over an algebraically closed field. So let's work over the algebraic closure of F, and actually, in fact, I think it's maybe almost time for me to switch to local fields. So what's going on is basically, yeah, we do want to have a global formula at the end, but for now, at every place, the same thing will happen. So I'm only going to think about finite places because, so it's going to be a non-Archimedean local field. Because basically the same thing happens at every finite place. Now, another thing that I should mention is that the Frankel, Langlands, and Go paper deals both with the function field case and number field case, and I will only work with the number field case. Even though, I mean, actually everything I'm explaining here will generally work the same in the function field case, but you know, the measure conversions have a bit of slightly different flavor, and things like regulators don't show. So. Okay, so yeah, so now I'm working over a local field, and for now I would like to just switch to the algebraic closure just for a moment. And so we have a Lie algebra, we have a Cartan subalgebra, and so then, well, so if we want to describe the space of, so Gx by conjugation, right? So G orbits on the Lie algebra. If you want, they will form a variety, right? And so they form an affine variety. And so if you want to find out the field of functions in this variety, then what we need to look for is the space of G-invariant functions, G-invariant regular functions on the Lie algebra. So that's the description that we want. And okay, so now the key point for us would be that you could kind of, it's of course the same as the W invariant functions on T. So, well, let's look at the, So let's first look at the Cartan subalgebra. So the while group acts on it, right? So notice that the conjugation by G action on the Lie algebra for the Cartan subalgebra just gives the permutations by the while group, right? And so what we're looking for is so let's put it this way. So these are the W invariant regular functions on T, and so these are our so these basically are symmetric polynomials, right? Because so you want it to be a polynomial function in the coordinates T1, Tn, right? That's invariant under the action of W. So in the case of GLN, that's the full symmetric group. So we're talking about all symmetric polynomials. As we know, in that case, all symmetric polynomials are generated, the algebra of symmetric polynomials is generated by elementary symmetric polynomials. And the same thing happens in general with the W invariant ones. So it turns out to be, in fact, so let's write it this way. So this the algebra of W invariant polynomials. And it itself turns out to be generated by elementary symmetric polynomials. I'll put it as W symmetric. They will actually come up, yeah, I think maybe I won't say it today, but there is a very precise, explicit description of them, which I will mention next time. So we need all this for the calculations in the second part. That's why I have to go into this detail. And so if you call this, so I'll suppose maybe, so suppose rank G is R. So then you have this elementary symmetric polynomials. Let's call them A1, AR. And so this rank turns out to be the same as just FW of A1, AR. And so then its spec is just the affine space. And this is our affine space of the characteristic polynomial, so to speak. So, so the upshot of all of this is that T mod W is isomorphic to spec F bar of A1 AR, which is the R-dimensional space. But this isomorphism is a bit non-trivial, right? So the map goes as G1, GR maps to these elementary symmetric polynomials. So, which in the GLN or SLN example, so then A1, well, A1 is going to be the sum, which is the trace, right, and AR. And the next one is pairwise products and so on, and the last one is the determinant, right? So it's the coefficients. So what we're seeing here is, all I'm saying is that the coefficients of the characteristic polynomial are symmetric functions in the eigenvalues. That's all we're seeing here. And so now, what is... Yeah, exactly. So this is a canonical map from T to T mod W. And Chevalley restriction theorem in this context can be stated as if you now take G invariant functions on G, it's actually isomorphic to W invariant functions on T. So if you take a polynomial here, you can just restrict it to T. And so it's called Chevalley restriction theorem because it says that this restriction is in fact an isomorphism. And concretely what it does is maybe, yeah, okay, so dually, so what we have is the G invariant functions embed into all G functions, right? And so now dually, when you take specs of this, what you get is you get the canonical map from G, right? So this is to T mod W, where each element maps to the unique W orbit in T, consisting of elements conjugate to the semi-simple part of X. Right, so when we have Jordan decomposition, which breaks every element into a sum of semi-simple and unipotent, right? And so the semi-simple one is in T that maps to T mod W, and so this is our map. And so the upshot is that for the Lie algebra, we have this completely canonical map, which I will call C, to the affine space of characteristic polynomials. And yeah, and maybe this is a good place to stop. So the next thing is, so this is basically our affine space, but however, I need to say a little bit more in detail about what happens for the group. And at the moment, all of this happened over an algebraically closed field, so there is a bit of interesting thing that comes up when the field is not algebraically closed. And so from here onwards, yeah, and so the next time we're going to talk about what this does for normalization of orbital integrals. If you want to think of stable orbits as fibers of this map, then you get a new, different measure on the orbits than the one that's used in the trace formula. And that kind of simplifies the Poisson summation later. Okay, thanks. Less questions?